So today I want to continue what we talked about yesterday, and we talked about transactions. And now let's think about how these things get a bit more complicated when you're thinking about them in a distributed setting. So the distributed transaction, it's a pretty simple definition. It's a transaction that involves more than one server. And as we've seen before, one of the big problems that you can get into here is your network being unreliable, being asynchronous. You get all the issues around the two generals and treachery with Byzantine type of systems come into play. So when you start reading papers that are very practical, like the System R paper, they actually get into all those different failure modes and start talking about them, how they get around them. And in any kind of transaction paper, that's an important part of it, because if you need to identify where all the places are that are most likely to fail, because if not, if you miss something, then your whole transaction system can go down at a probability that's higher than what you're willing to accept. So in the case of distributed transactions, you want similar type objectives as before. You want consistency, you definitely want fault tolerance. Performance is still important, and performance becomes more difficult to achieve because of the distributed nature. All of a sudden you have this network delay around. And availability. Just let me repeat that piece about performance, the network delay. That's one of the big performance bottlenecks now in getting our transactions to run. If you get network delays in the milliseconds, right, that automatically starts limiting what the transaction rate, the processing rate that you can have is. If something is 10 milliseconds, how many transactions, if you have to wait 10 milliseconds for network delay, let's say per transaction, what does that limit your transaction processing speed to? 100 per second, right? What if it's 100 milliseconds? Now we're starting to talk about longer term hauls across the US. That's in that range. Now you're down to 10. Now you have to coordinate with a bunch of different servers. There's all these network delays there. So when you read about something or think about something that has to do with distributed transactions, make sure you take into close consideration how many messages are going to be sent back and forth and what kinds of latencies you expect, because that's one of the very real bottlenecks here. So what kind of model are we going to use for our transactions? Well, let's think about nested transactions. Since we talked about those yesterday, they're hierarchical. That model tends to blend really well when you think about with distributed transactions, because the hierarchical model allows you to distribute the computation amongst a variety of servers. It's a programming paradigm for doing that. Now, as we saw before in this model, you have a coordinator who then goes off and sends out sub-transactions to what could be other coordinators of those sub-transactions, and so on down the line. And at some point at the end, you have some leaf nodes. And this tree doesn't have to be balanced. It can have a variety of different configurations, but the more balanced it is, the more distributed the nature of your parallelism. So we also have to think about a failure model. Well, here's a simple failure model that covers almost everything that tends to be important. One is asynchronous communication. So again, the network is unreliable. It's hard to tell the difference between a server, something that's crashed before you sent the message or after they sent the acknowledgement. You can have servers fail unexpectedly. They do, unfortunately. Now this third one is a little bit is a simplification, which is that in the rest of this, we're going to assume that the servers are going to send the right message. There's not going to be this Byzantine or treachery involved. If you do think that there's going to be treachery or some kind of bugs in the system like this, then it adds another level of complication to the whole distributed transaction. But if you want to approach solving that issue, you can take what we learned before about the consensus problem and build some of that infrastructure into the transaction infrastructure. But as it is, because they're two separate ideas and they have two different approaches that can be combined, I'm not going to bring that in here, and I'm not going to overlay it in the slides that follow. So let's take a pretty straightforward example of how you might do a commit. So before, if you're in a single processor and you're running a transaction, remember we talked about commit. commit can be done locally, and you can make certain assumptions. For example, that that the processor isn't going to blow up, or that the communication between the processor and memory isn't going to go, going to take forever. When you get into a distributed type of transaction, those kinds of assumptions come out because now you have this, for example, the communication issue. So let's just take the simplest one so we can analyze some of the problems with just taking a straightforward approach. In a one-phase commit protocol, you have a coordinator who sends out a commit or an abort message request to all the participants in a transaction. So there's been some nesting already, people have done their work, and then the coordinator says, okay, let's commit. What the coordinator expects is that everybody out here who gets the commit message is going to commit their transaction so everyone else can see it, and it's going to reply back and say, okay, I'm all done. And so the coordinator here, once he hears all the done messages, done, 1, done 2, done n, it's going to say, okay, well now all those things are done, so now I'm done. So this is the kind of, imagine that you were doing something like transfer of a bank account, right, or transfer of money from two different banks, 2 different accounts. Well, there would be 2 of these, right? A withdrawal somewhere out there and then a deposit somewhere else out there if you were the third party mitigating this thing. Now, in the one-phase commit, I mean, it makes a lot of, it's pretty straightforward. You can use timeouts or something like that if you don't hear this message back. If you don't hear the done message after 5 seconds, you might send another one saying, hey, are you really done or not? One of the big problems that you have here, though, is that this commit has to be done it has to be an all or nothing, right? Because this is supposed to be a transaction, and it's a unilateral decision. But it's unilateral because this coordinator says do it, and none of the participants can say, oh, forget it. Okay, and why is this important? Well, imagine that you were trying to do this protocol, and then somebody out here got cut off from the network. Okay, so you're trying to do this bank account transfer. You're sitting there at the bank, and the bank computer goes, you tell the teller types it in. Everything seems to be going okay, and then all of a sudden the commit's trying to happen, and this computer here gets cut off. And it's the one that's going to do it could be either half of the transaction, a deposit or withdrawal. Well, how long is it going to take for this done to come back at this point? Assuming that this machine will get put back on the network at some point. Arbitrary. It could take hours. Do you really want to be sitting over here waiting for hours for this thing to come back up? Wouldn't you rather have the teller say, oh, it didn't work. We want to try from a different account? But if in a one-phase commit here, if you did that, if the teller said, oh, let me try from another account, what happens when this one comes back up? And it's assuming that it's gotten the commit message. So it's going to do so you're going to have you're going to have an extra transaction happening here. Oh, and by the way, these other guys and the other participants might have already committed too. So then you're kind of stuck. And so you can have these long delays as one big issue. There can be other problems that happen along the way here that will cause similar types of performance or just practical issues that make this algorithm something that you don't want to try when you have a distributed system. So now let's see how we can modify this one-phase protocol to actually get around some of these issues. How many of you guys have heard of two-phase commit? Okay, this is a very common, this is one of those words that you'll see in modern papers thrown around as two-phase commit. And it's a piece of terminology that is expected that you'll know what it means and what its implications are. So the idea here is that any participant in a transaction can request that a transaction commit or abort. Now typically this will be some kind of coordinator that says that. So again, you're in the situation, you go out there, you start a transaction, there's all these nested transactions, they go off and do their thing. Remember, there's the notion of the provisional commit that we talked about yesterday. Some of these nested transactions can abort, like we talked about yesterday, and the coordinator can try other ones to try to get around that. But in the end, you'll be in a state where the whole thing either has to finish, to commit or to abort. So there's two phases. In the first one, it's a voting phase. And what happens there is that all the participants in this transaction are asked to vote whether they can commit or not. So they'll either send back a message that says, yes, I can commit, the vote will be commit, or no, I have to abort. Now the set of these participants in this case don't include someone like here, if this one failed, if this nested transaction failed, if the coordinator just substituted this one instead, this branch here isn't included in that voting phase because it doesn't matter, right? It already aborted. So you take everyone who matters, and those are the participants, and they all vote. Now, if someone says yes, I can commit. If any participant says yes, one fail-safe measure that you take is the state of that process, or rather, more specifically, the state of the changes that transaction is going to make. Those should all be saved into some non-volatile storage. So you take everything like what its variables are that are going to change, or objects, their new values, some kind of transaction ID, those kinds of components. You save them to non-volatile storage. Now this takes time, but what does it buy you? Reliability, good. So if you go back and you vote yes, and then you crash, and then when you come back up, you'll still have this information, so you'll still be able to carry out this commit if indeed everybody decides to. And that gets into the second phase. In the second phase, if everybody says yes, it has to be unanimous, then the coordinator tells everyone, okay, go ahead. Now we've all decided to do it. Let's do it. Let's commit. If any one of them aborts along the way, then the coordinator tells everyone, let's abort. So in the case of this, let's take the two-phase commit in the example we had before. Suppose that they went through and started asking everyone, can you commit, can you commit, can you commit? And then let's take a couple cases. One is that the message to asking to commit doesn't get to this one because there's a network break. Well, now how do you solve that? Well, you can just say, well, after about a few seconds, the teller can type in, abort and try something else, and everybody's happy. What happens if you get this message here, and this one says yes, and then gets it back, and before it gets back, there's a network break here? Well, if you don't hear back, and you can use timeouts to try to get around lost messages, but if your time runs out, then you can just always say, I'm going to consider this, I'm going to tell everyone to abort, and I'm going to ignore this message when it comes back. And at that point, everyone's still happy because we can get through this and try something different. What happens if this yes message gets through, but then the commit message doesn't get through because the network's down? Well, because all this information is saved and this guy's ready to commit, when the message eventually does get back through, then it'll just finish. But at this point, the person who did the transaction can assume that it was done. And as we talked about yesterday with logging, remember how we had the old version and the new version and that kind of and locking of resources? We can use that type of mechanism to make sure that these objects that are being modified are being locked, or you have some kind of mutual exclusion so someone else doesn't come over and try to get them. So that's one trade-off, that there is a performance issue if there is a network blockage keeping you from getting that last commit or abort. But that's a pretty reasonable trade-off in this example. So this two-phase commit is actually, there's a lot of folks, a lot of systems that use it. In the book, you can read about a three-phase commit, which gets around some of the performance issues here. But already we've gotten around our biggest one. And as we talked about yesterday with logging, remember how we had the old version and the new version and that kind of and locking of resources? We can use that type of mechanism to make sure that these objects that are being modified are being locked, or you have some kind of mutual exclusion so someone else doesn't come over and try to get them. So that's one trade-off, that there is a performance issue if there is a network blockage keeping you from getting that last commit or abort. But that's a pretty reasonable trade-off in this example. So this two-phase commit is actually, I mean, there's a lot of folks, a lot of systems that use it. In the book, you can read about a three-phase commit, which gets around some of the performance issues here. But already we've gotten around our biggest one.
What kinds of real-world systems would be examples of distributed transactions like this?
Okay, so one of them, let's see. Let me think of. I'm going to try to think of some now, but I don't have a paper in front of me that lists like a dozen of them. Let's think about.
Credit card transactions. You have to go from the credit card processor to a bank through merchants. Yeah,
the reason credit card transactions is the reason. Yeah, credit card transactions is an example where you can have another party, because you have these you have the bank, and then you have the merchant bank, and then you have the person who's trying to run the transaction. So there is someone else who's added in. I was trying to brainstorm something where there's like dozens of people involved in getting something done. Let me think about it. Because like nothing comes off the top of my head.
Stock trading?
Stock trading.
I don't know how that works. So
yeah, I don't either. So I don't know the details of how they run that. I mean, can anyone come up with an example of where there's a lot of stuff that has to go on to a lot of participants that have to all agree on? Mm-hmm.
Like a date calendaring thing when you're trying to set up a meeting.
Oh, that's a great one. I love it. Okay, that's awesome. Calendaring. Real good. So if you're trying to set up a meeting on everybody's calendar, then suppose there are like 5 different participants and they're all over the place, and you have to go and their calendar becomes this resource that you then have to pre-allocate potentially a space on. So in this case, the object might be something like the 11 o'clock slot on next Tuesday on someone's calendar, and then the final commit is what actually this is equivalent to penciling it in, and then committing means you put it in an ink. Great example, thank you. Yes?
How big is the performance sacrifice that you take by saving process?
By writing this thing out? It depends on how big these records are, and it also depends on how you've structured where these are. Like if they're in memory, for example, you're going to have to it's easier to access and find them and write them out. We'll see later on that sometimes you put these in logs, and if they're in logs and it's a sequential structure, then you have to go through and find all the right things that you want to save out. So it's a little bit more of a performance hit. So it depends on the medium that you're accessing from memory or or something like a disk file. And second is how they're structured and what the order, how good the algorithm is for accessing this information and putting it all in one place. We'll see later on that because these are running a lot of transactions, that there's a lot of these pseudo states that are going to need to be saved, and then going through there's data structure algorithms types issues that you have to address in order to answer that question fully. I mean, let's take the second look at this nested transactions with the two-phase commit. Remember before when we were thinking about the nested transactions, we talked about locking, simple locking, having locks on pieces on resources. Now, one of the problems with locks and with this mutual exclusion is that they introduce a level of complication to this two-phase commit, and part of it is that when you have someone let's say this coordinator running, it's possible that this coordinator here could be accessing some of the same structures that some of its leaves or some of its descendants are accessing. So one of these might go off and say they read some value, and based on that value they might decide how to structure the nested algorithm that it's going to use. And go that way. So in the date book example is a good one. Imagine that you're this coordinator here, and you're supposed to grab 3 of the 5 executives for some important meeting. So what this guy can do is, as part of its transaction, is say, well, let me see if these slots are available, boom, boom, boom. And if they are, then it picks 3 of them, and then it goes off and forks off nested transactions to go to the servers of the people's date books and do the appropriate, make the appropriate changes. But now you notice there's a read that's happened here, and then there's going to be a write that's going to happen over here. So you can see that there's some amount of complication that comes in, because now that resource is locked over here, so anyone else along the line over here has to deal with those locks. Did you guys read that the section about locking in the? Okay, good. So you know that you can control the granularity of this and the performance impact using the intentional locks, and that matches well with this hierarchical nesting structure. So there's a couple ways that that you can coordinate all of this, so that to make sure that all the resources are locked and unlocked correctly, and that the commit part of it actually works. So a couple of algorithms. One is a hierarchical one, and in the hierarchical one, what you do is when you're asking for people to vote, the coordinator will go off and ask whoever matters, which is in this case this one and this one, yes, commit or abort. We won't ask this one because this one's already aborted and it doesn't matter. Then you just propagate that down, so it's just a recursion. These will go off and ask the people that it cares about, commit or abort, and then it just goes all the way back down, and then it comes back up. Now the nice thing about this algorithm is that it's very distributed and very simple, right? You just shoot it out there and then you wait from these two and then it comes back. You may need, if you want a deeper level of control, there's what's called a flat algorithm. In the flat algorithm, the coordinator knows who out here at the end has provisionally committed. So basically has said, I'm ready to go if you are. So what it does is it goes off and it says, okay, for those who have provisionally committed, who are ready to commit, I'm going to ask them, okay, now let's do this 2-phase commit to do the full commit. Let's ask you if you vote yes. Now one of the issues there is, imagine that in this case, one of these here provisionally committed and one of these here aborted. And that's why this guy aborted. And that's why you got the abort and you had this other branch over here. If this coordinator here just takes the list of everyone who's provisionally committed, it's going to see this one here and say, oh, that's on my list of people who have provisionally committed. But remember when we described our 2-phase commit, we said the only participants are the ones who really matter, which is like this one here, one of these over here. Does this one really matter whether they? No, right? Because this guy aborted, this one should be aborted also at some point. So the extra complication that you have here, if you have this using this flat algorithm, is that you have to have the provisional commit list, plus you have to have the abort list. And so you have to know that this guy aborted, and you have to know something about the tree structure or the nesting structure. You have to know enough that you can deduce that this one this node here that provisionally committed eventually is rooted at a coordinator who aborted, who doesn't matter. So if you have these pieces of information, then you can determine what's the list, who out there has provisional commits, and then you can go out there to 2-phase commit algorithm. Now, why might the flat one? It seems a bit more complicated. You have to know more things. What's the trade-off there? What do you get out of using that one versus the hierarchical one? Yes?
And maybe avoid time sending the messages up.
Performance. Right? Here you have all these messages going back and forth, this whole structure. Here you just communicate with, what may be a handful of these guys at the ends.
Might you also have a little more fault tolerance because you don't actually have to worry about whether or not the guys in the middle stay up or not?
Yep. That's another thing that you get. You get cutoffs, cutoffs at different points in the communication. So let's say this one here provisionally committed and this one didn't, but it's enough to make this one provisionally commit. If communication gets cut off here and here, you're all set as long as you have some other route to get to there that this one may not have. So you get optimized communication. So remember, these round trip times, these number of messages, they're a big consideration in these protocols. So the flat one gives you some control over that. You can even, if you're really concerned about it, you can start digging down into the network layers and trying to figure out how you can best get around any congestion patterns that you may have seen, that kind of thing. So there's all sorts of ways you can optimize them, and there's papers you can read about different approaches to optimizing under different kinds of conditions.
So the list of provisional commitments is all the leaves, or the leaves that matter?
Yeah, anyone who's provisionally committed. The list of provisional committed folks is anyone who's done a provisional commit at all in this nesting. And in this case, if you're a coordinator and you're not doing anything, then you're not part of that list. If you're someone down here who has access to an object, and you've actually made some state changes to an object, then you're part of that list. So that's another way to think about it, is really the people who matter are the ones who control these objects, who are sharing these objects. Right? Because that's where the locks that's where you have to do the locking, that's where you have to do the i.e. mutual exclusion, that's where you have to make the changes. So once these other folks over here, for the most part, are just managing the whole process and coordinating it. The people who are actually going to do the commit, when you get down to it, are going to be the ones who change the value of that shared resource, change the state that then can be observed by the rest of the system.
It just seems to me to even be able to generate that list, you're doing a hierarchical thing anyways.
Yeah, and there are some messages that are going to have to go back and forth anyway, because you're going to, when you're nesting the transactions, you're going to have some communication. You already have to have some communication this way, saying I'm nesting. I mean, here, go do this. You're already going to have some this way, where there's packets going out and potentially ACKs coming back. And as soon as you have any kind of traffic coming back for any reason, like an ACK, you can always start piggybacking stuff onto that. So you can remember, piggybacking is if you're sending a packet, the overhead of composing the packet and putting it out is pretty high, but if you just want to add a few more bits onto it, that's got a low marginal cost to it. So if you can start adding some and piggybacking on this communication that goes back and forth, you can start building up this list based on the existing communication already. The other thing you can do is you can imagine if you're doing the flat, and I'm just brainstorming different ways that you can implement this. Imagine that the coordinator sends out its IP address or its domain name, and imagine the protocol said anyone at the end here, if you provisionally commit, you have to send a message back to this guy directly. I mean, that's another way that you could build this list up that shortcuts having to go through all of this. So it depends on the system that you're building, but we can sit here and probably brainstorm a few other ways that have different trade-offs. So do you guys understand the difference between the hierarchic and the flat? The book goes off and explains it also, and they have examples. So if you want to see another example, you can look there.